Hello, everyone. I'm going to talk about our paper on the Symmetric Sparse Boolean Matrix Factorization and Applications. It's a joint work with Sitan Chen from UC Berkeley, Zhao from Adobe Research, and Runzhou from Columbia University. Here's the outline of my talk. First, I will give you some backgrounds on non-negative matrix factorization problems and its variants, and also some motivations from theoretical computer science and machine learning. Then I'll show you our main results. Next, I will tell you some techniques of designing an average case algorithm for sparse non-negative matrix factorization, and also in analyzing the non-singularity of sparse Boolean matrix. Finally, I will show you some open questions. Let's get started from the introduction. So what is the AMF problem? Here's the definition. Suppose you are given a real matrix M with dimension n by m and also a rank parameter R. You need to find two matrices, W1 and W2, with non-negative entries, such that for n by R matrix W1 and m by R matrix W2, the distance between W1 times W2 transpose and M is minimized. Here, the distance metric can be L0 norm or the F norm. This problem has been studied over decades and has many applications in different fields, including image segmentation, document clustering, or even music transcription. An NMF has some important variants. The first kind of variance is the symmetric NMF, which means the two factors W1 and W2 should be equal. This problem relates to the kernel k-means and also graph clustering. The second kind of variance is a binary valued NMF, where W1 and W2 should have binary valued entries. For example, 0 or 1 or plus minus 1, which relates to the LDPCQ or graph partition. The third variance is the sparse NMF, where we restrict W1 and W2 to be row sparse or column sparse. In our paper, we focus on the problem that has all of these three kinds of variants. That is, we study the sparse symmetric Boolean matrix factorization problem, or SSBMF problem. Here's the formal definition. Suppose you are given a symmetric matrix M and of dimension n by m and a sparsity parameter k and rank parameter r. You need to find a row k sparse matrix W in m by r dimension, and also with Boolean entries such that the L0 distance between M and W transpose is minimized. Why should we care about this problem? Because it has many important or natural motivations from theoretical computer science and machine learning. The first ITCS motivation is the Clique decomposition problem. Here, we regard the input matrix M as the adjacency matrix of a graph key. Then the factor W just encode a clique cover of G, which partitions the edges of G into several cliques. Note that the jth column of W indicate which vertices belongs to the jth clique, and the sparsity parameter K as a constraint that each vertex should belong to exactly K cliques. This is an example of a graph with 9 vertices, and we partition it into 6 cliques, and each vertex belongs to exactly 2 cliques. If we solve SSBMF, then we will find such a clique decomposition, giving only the adjacency matrix of the graph. And this problem can be used to identify community structure of a social network. The second motivation in TCS is about the line graph of hypergraphs. Here we regard W as the edge vertex incidence matrix of a K-uniform hypergraph with M hyperedges and R vertices, then the input matrix M is just the adjacency matrix of the line graph of H, where the line graph is the graph with vertices corresponds to the hyperedges of the hypergraph H, and the two edges are connected in the line graph if and only if they have some common vertices in the hypergraph. In this setting, SSBMF asks for reconstructing the hypergraph from its line graph. Notice that this problem is parameterized by an important factor K. When K equals to R, the hypergraph becomes the graph, and this problem was fully characterized by the witness isomorphism theorem. And many efficient or even nearly linear time algorithm has been proposed to solve the reconstruction problem. Unfortunately, when K is greater than 2, no such theorem exists, and even determining whether a given graph is the line graph of some K-uniform hypergraph is NP-complete problem. It turned out to be a worst-case hardness of SSBMF problem. So if we assume P not equal to NP, then we cannot hope any polynomial time algorithm to exactly factorize giving an arbitrary matrix M with the condition of SSBMF. We also found some motivations in machine learning. So if we solve the SSBMF problem, then it will imply some attacks on the InstaHide scheme, which is the scheme for previously training neural network on images, while have little effect on the training accuracy. It constructs the synthetic training data using some random K-linear combinations of K private images. After this scheme was proposed, some attacks on this scheme were also proposed, and they are implicitly use the SSBMF problem. Roughly speaking, they showed how to form the so-called gram matrix M, whose ij's entry indicates whether the sets of private images that give rise to the synthetic image I and J overlap. Then the optimal solution W will tell you which private images were used to generate each synthetic image. And this kind of information is very helpful to recover the private images from the synthetic training image. Also, the attack algorithm implies the average case algorithm for SSBMF, because each synthetic image is generated from a random linear combination of private images. However, these algorithms are either heuristic and lack of provable guarantees, or only works for certain parameters. In our paper, we focus on the average case SSBMF. Namely, we assume that each row of the ground truth matrix W is an independent, uniformly random K-sparse Boolean vector, and we form the input matrix M to be W times W transpose. Here, the matrix multiplication is over Boolean semi-ring, where the addition operator is the logical OR, and the multiplication operator corresponds to logical AND. We show that when the dimension of M is large enough, then there exists an algorithm that takes as input M and runs in O of M to the omega plus 1 time, where omega is the matrix multiplication exponent. Then with hyperability over the randomness of W, it will output a matrix W hat, such that the columns of W hat equals to the columns of W up to a permutation. Second, we also give a worst case guarantee for the approximate SSBMF, or even sparse NMF. So suppose you have a symmetric matrix M with integer entries and a rank parameter R and some accuracy parameter epsilon. Then there is an algorithm that runs in quasi-polynomial time and output an epsilon approximate matrix W hat such that W hat is zero k-sparse. And the distance between W hat transpose and M is only epsilon times M squared worse than the optimal solution. Here, the matrix multiplication can be either over integer domain or over the Boolean semiring. And we know that our algorithm is based on a quasi-polynomial time 2CSP solver proposed by Ruizhe and Moshkowitz. As a consequence, our algorithm also implies an algorithm for the best k-vector sum problem. Here's the definition. Suppose there exists a hidden dataset X consisting of R d-dimensional vectors x1 to xr. However, we are only giving access to some other m vectors y1 to ym, with the promise that each y vector is generated by first choosing a set S of size k and sum of all the vectors of X in this set. And the goal of the BKV sum problem is to recover the sets S1 to Sn. Moreover, we assume that we are giving access to a similarity oracle, where with the input I and j, the oracle will tell you the size of the intersection between sets Si and Sj. Also, we assume that each set Sj is uniformly random k-subset. It's easy to see that this problem is quite close to the SSBMF problem. And also, this problem is a mathematical abstract of the attacks on InstaHide. By our average case algorithm for SSBMF, we can show that for a BKV sum instance, together with its similarity oracle, there is an m to the omega plus 1 plus d times r times m time algorithm that approximately recovers the magnitude of the heavy coordinates of every vector in the hidden dataset. Here, we say a coordinate is heavy if its magnitude is omega k times the average value of any original vector in that coordinate. So we can not only recover the sets S1 to Sm, but we can also extract some information from the hidden dataset. Now let's switch gear to our average case algorithm. In the SSBMF problem, we are giving access to the matrix M, written as W times W transpose, for some W that we want to find. But it can also be written as the sum of each column of W. We say Wi tensor product, Wi tensor Wi, where the multiplication and addition operations is over the Boolean semiring. Now, suppose we can form a three-dimensional tensor T, which is Wi tensor Wi tensor Wi, over the integer domain, and we further assume that each column of W is linearly independent over the real. Then we can simply run a standard tensor decomposition algorithm, for example, the Yang algorithm, to recover W1 to WR up to a permutation. Therefore, Based on this high-level idea, we will have two technical steps. The first is to bootstrap the tensor T, giving only the matrix M. And second, we need to show that the columns of W are linearly independent with high probability. Let's first look at the first step, bootstrapping the tensor. Namely, we need to bootstrap third-order information, Wi tensor Wi tensor Wi, from the second-order information given in M. Let's consider the BKV sum setting, where each Wi indicate whether the vector J is in some hidden set Si for some K subset Si. Then we can interpret an entry of the tensor T as the size of the intersection between SA and SV and SC. In the same sense, the matrix M tells us whether two subsets intersect. Now the question becomes how to estimate the size of triple intersections, giving only some indicators of the intersection between two subsets. The first step is to apply some inclusion-exclusion principle to express the intersection between three subsets as some unions of three or two subsets. Then we give a method that can compute the size of any L subsets union for any L. We first look at the probability that a randomly chosen K subset of R does not intersect any of the L subsets S1 to SL. By simple combinatorics, we can show that this quantity can be computed by this formula, which does not depend on what exactly the subsets S1 to SL is, but only depends on the size of the union of them. So we denote it as mu sub the size of the union. Then, by an observation, we show that when R is large enough, mu sub T is a monotonically decreasing sequence, and they are also well separated, which means if we can estimate mu sub S1 to SL's union within some error of order K over R, then the size of the union can be exactly decoded from our estimate. So how to estimate this probability? Notice that each column of the input matrix M gives a sample of a random K subset V, and V has no intersection with S1 to SL if the entries in these corresponding rows are all zero simultaneously. Therefore, we can just count the fraction of such columns in M to estimate mu with high accuracy as long as the dimension of M, or in other words, the number of samples, is large enough. Here's the pseudocode of our main algorithm. It consists of two parts. First, we form the tensor T using the previous slide's approach, and then we run the standard Ruizhe algorithm on the tensor T. What is the running time of our algorithm? For the first part, the time-consuming step is to estimate the probability mu sub A and B and C. Naively, it will take M to the fourth time. By using some batch techniques and fast matrix multiplication, it can be improved to O of M to the omega plus 1 time. And for the second part, it is known that the Ruizhe algorithm can be done in M to the omega time. Therefore, our average case algorithm takes M to the omega plus 1 time. What about the correctness? The correctness of the first part was already analyzed in previous slides. For the second part, in order to correctly decompose the tensor, the Yang algorithm needs the columns of the ground truth matrix W to be linearly independent. How can we show this happens with high probability? So we need to analyze the non-singularity of sparse Boolean random matrix. Before looking at the sparse case, let's consider an independent case where the matrix is generated with independent plus minus 1 or 0, 1 entries. Then what is the probability that the matrix is singular? It's an old mathematics problem, and it was shown to be little o of 1 in 1967, and then it was sequentially improved to 1/2 plus little o of 1 to the r, which is believed to be a right upper bound. In our case, however, the entries of W are not fully independent, but there exists some dependence within the row, since we require that the row sum equals to k. In the dependence setting, there exists some works that study the dense case, which means the sparsity parameter k equals to omega of log of r. And for the constant k, it was conjectured that the adjacency matrix of a random k regular graph is singular with probability little o of 1 for k at least 3, and it was fully resolved in a recent paper. However, it's still a little different from our setting, since our W corresponds to the adjacency matrix of a random bipartite graph with only left singularity, but not left and right singularity. So here's the definition of our problem. Let W be a matrix whose rows are IID random vectors, each following from a uniform distribution over 0, 1 to the r with exactly k ones. Then for constant k, what is the singularity probability of W? Or equivalently, if we want to achieve the singularity probability to be little o of 1, how small of m can we choose? We remark that by a simple net argument, when m is at least r squared, then the matrix W is not only full rank, but also polynomially well conditioned. However, we want to achieve nearly optimal sample complexity. So how can we improve this naive lower bound? We first consider the case when k is an odd number. Then we observe that the linear independence of the column of W in R can be reduced to the linear independence in F2. Therefore, we only need to compute the probability that W is singular in F2. And we show that when M is at least R over K times log of R, then with high probability, W's column will be linearly independent over F2. And then by the reduction, also linearly independent over R. How can we prove this? It's quite straightforward. We just need to bound the probability that W times U equals to 0 for some U in F2 to the R, and U is not equal to 0. And this probability can be bounded by the sum of probability that for some U with exactly lambda ones, the matrix W times U equals to 0. And we denote it as P of lambda. And this quantity is related to the binary cross-choke polynomial, which has some known upper bounds for the magnitude. And then we combine them together, we can get the upper bound for the singularity probability of W over F2. The second case is when K is even. However, the previous approach doesn't work because for all one vector, W times 1 equals to 0 for any W over F2. In our paper, we adapt some techniques in a paper by Faber, Cohen, and Solomon, where they study the dense case and we adapt their techniques to the sparse setting. Suppose we want to compute the probability that W is column singular. Then we consider two cases. The first is Wx equal to 0 for some x with support of size less than r. And the second case is Wx equal to 0 for some x with full support. For the first case, since the bad event is W times all one vector equals 0, and since the x does not have full support, then it can still be reduced to the F2 case. And for the second case, when x has full support, we use the techniques in the SKS 20 paper to look at the fiber of the vector x, where the fiber means the set of all indices whose entries are equal to a particular value. When x has a large fiber, which means most of the entries in x are the same, then it can be easily upper bounded by some simple estimates. For the second subcase, when x has only small fibers, it's a little tricky. We use some tools in group theoretic data would offer inequality to upper bound the anti-concentration. And also, we use a trick in FKS 20 that transforms the distribution of a Bernoulli random vector to a distribution of random k-sparse vector. Put them together, we can show that when M is at least max of R and R over K times log of R, then with high probability, the columns of W are linearly independent over R for even K. Now combine the even and old case together, we can show that for any W with zero k-sparse, as long as M is large enough, the columns of W are linearly independent over R with high probability. Then this theorem implies that the assumption of Young-Rich algorithm will hold for most of the random W, which proves the correctness of our average case algorithm. Finally, let me tell you some open questions in our work. So we have an M to the 1 over epsilon times k squared times log of R time algorithm for the worst case approximated SSBMF. And we also show that for the exact version, it is NP-hard. So can we improve the runtime to some arbitrary function in terms of KR and epsilon times polynomial in M for the approximated SSBMF? Or can we show that it is impossible by proving the hardness of approximation for SSBMF, probably based on some fine-grained hypotheses like exponential time hypothesis, ETH, or gap ETH. We know that the prior work by Aroa, Kalin, and Moitra has some NMF algorithms and lower bounds, and their techniques might be helpful to resolve this open question. The second open question is related to the batch k-vector sum problem. Our average case algorithm implies an average case algorithm for batch k-vector sum, which has some applications in machine learning security. So can we find more applications of the batch k-vector sum problem in cryptography? And on the other hand, the batch k-vector sum problem is closely related to the k-sum problem, where the average case hardness of k-sum was recently proved. What about the average case hardness of batch k-vector sum? Thanks for your time.